Hello, welcome to Functions Day 3. We're going to use the power rule for derivatives. So last class, we worked on that formal definition of the derivative where f prime of x was equal to the limit as h goes to 0 of f of x plus h minus f of x all over h, which we've done many times throughout the year because I asked it on many quizzes and tests. And at the end, we plug in h equals 0, and we've got a nice little expression. Well, today we're going to take more derivatives, or what we call f prime of x, or y prime of x, or dy over dx. Those are our main ways of writing something as the derivative. We're going to learn a rule today on how we do it for power functions. So let's talk about something that's easy. A function that is just a number, just a constant number. F of x equals 5, or y equals 5, which is just a horizontal line. So maybe just something like this. That's a line y equals 5. Well, what's another word for derivative? That is slope. The derivative is like the instantaneous rate of change or the slope at a point. So according to this model, our slope for this horizontal line is 0. That means my derivative is 0. That means anytime I have my function is equal to just a constant number, its derivative is 0, or y prime is 0, or dy over dx is 0. Okay, so today we're going to look at things of power functions. A times x raised to some n power, where a is the coefficient up front, n is the exponent of the power, and we did some of these last class. So the derivative of x squared turned out to be just 2x, or the dy dx is called 2x. dy over dx, change in y over change in x, slope. And x cubed, again we did last class, we turned that out to be 3x squared, or the dy dx is 3x squared. Is there a pattern? Well, let's see. Is there a pattern going on? Well, I think yes, there's definitely a pattern. I'm going to talk more in detail, but it looks like something's going on with the coefficient and the exponent. Some relationship between them, and it looks like the exponent is 1 less than before. Look, we went from x squared to x to the first. We went from x cubed to x squared. So we're going to have to look to see what's going on. So we have other examples from last class. We did 2x squared minus 3x plus 4, and we got 4x minus 3. And really what's going on with this one is this is really 3x to the first, and now this is really, even though we don't write it this way, it's really 3x to the 0, even though we don't write it that way. And then this one was 3x squared minus 10x plus 4. So let's see, what is the pattern? Do we recognize a pattern? So are we seeing a pattern when we have this power function, a times x to the n? So when we take its derivative, this is what's going on. It is going to be that coefficient multiplied by that exponent. And then it is going to be x to the n minus 1. So what's going on? The exponent loses 1 degree. So we have something called a power rule for derivatives, or what I'm going to call a shortcut rule. Instead of doing that long x plus f of x plus h minus f of x over h and doing all those steps, we have two little easy things. One, if f is just a constant, if it's just a number, its derivative is equal to 0. So the derivative of 5 is 0. The derivative of negative 18 is 0. That's easy. But when we have a function that is in this form, the power function form, its derivative is going to be the coefficient times the exponent, and that's what this a times n stands for. And we lose right here, we lose 1 degree off the exponent. It goes down by 1. So every single time I'm going to do my coefficient up front times my exponent, and sometimes you got to multiply fractions, and 1/2 times 4 is 2, and x to the 4th loses 1, becomes x to the 3rd. I'm going to do 5 times 3, and I get 15. X to the 3rd becomes x squared, and 2 times 6 is 12, and x to the 6th becomes x to the 5th. That is the derivative of those very simple power functions. Well, what happens if we have a polynomial function, or a function that has many terms in it? Everything we've been doing has been a single term for the most part. Well, we just do one term at a time. So when I see this example right here, I just do 2x to the 6th is 12x to the 5th plus 2x to the 3rd plus 15x squared. And this last term says 6, and that's just a plain number, and the derivative of a number like 6 is 0. So this is the derivative, or f prime. You see above, sometimes they use y prime or g prime, but f prime of x is equal to this expression. So we had some examples that you could try on your own, and like I said, all you do is take coefficient times exponent, and I lose a degree. The big key here is notation is important. I want to see that f prime notation or g prime or y prime notation. This example here was really x to the 1st, so y equal -5, 6 x to the 1st. -5 times 1 is -5/6, and then it becomes x to the 0. I don't write down x to the 0. It just becomes what it is. So what happens if we have a fraction for our exponent? A power function does not have to have a whole number or an integer as an exponent. It could be a fraction. Does anything change? No. No. It's the same rule. Nothing has changed. The only thing that's going to change now is we have to remember how we do subtract 1 from a fraction, because when we do our exponent, we have to subtract 1. Well, if you go back to whatever grade you did this, instead of writing it 1, you write it as 3/3, and 5/3 minus 1 is really 2/3. If you had -3/4 and you want to subtract 1, well, you're going to rewrite that. Instead of -3/4, you're going to write it as 4/4, and you get -7/4. But I have a nice little pattern that I see here. If I rewrote this as b/b, it becomes a minus b/b. Okay? Or better yet, what I really see is top number minus bottom number over the bottom number. Or what I really see is numerator minus denominator over the denominator. In all these examples, the denominator never changes. So if you do 5/3 minus 1, really all you do is 5 minus 3, which becomes 2/3. Or -3/4 minus 1, well, I really do -3 minus 4, which is now -7. Again, still over 4. That denominator won't change. I'm just changing the numerator. We have more examples that we could do, but the pattern is the same. I'm going to do coefficient times exponent, and I get 12/2 or 6. And now I'm going to do x, and 3 minus 2 is going to turn into 1/2 of my exponent. Again, -12 times 1/3 is -4, and 1 minus 3 Means my exponent is now negative 2/3. And then finally, this one, well, 2 times negative 5/3 is just negative 10/3. It doesn't reduce anything. And then I'm going to do negative 5 minus 3, and I get x to the negative 8/3. So here are my three derivatives that go. Notation is important. F prime equals 6x to the 1/2, and so on and so forth. Well, how about when I have things that don't look like they're in power function form, like 4 over x cubed, or 6 times the square root of x? Well, this is the key. I need to rewrite things. I can only take the derivative when I rewrite it in that power function form, a times x raised to an exponent. So when I see 4 over x cubed, I rewrite it as 4 times x to the negative 3, and so on and so forth. So we need to go over our rules of exponents and how we rewrite things as power functions. So one of our first rules is a over x to the n, well, something like 3 over x squared is really 3 times x to the negative 2. Because something with the denominator is really x to a negative exponent. So something with x in the denominator is really x raised to a negative exponent. Or if we have something like 5 times the square root of x, well, that's really 5 times x to the 1/2 power, because the square root is the half power, or this root is that denominator. And then our last example of rewriting is a number times, and we have a root and a power. So something like 2 times the 5th root of x cubed, I rewrite it as 2 times x to the 3/5, because my fraction that I make for my exponent is power over root. These are key. I cannot take derivatives unless they're in the form a times x raised to an exponent. So I have a bunch of examples here, and the first thing I have to do is rewrite them as power functions, and then I could take its derivative. So first I rewrote every single one of them to have x raised to an exponent, and the same rule applies. I'm going to do coefficient times exponent, negative 12, x, but I'm going to subtract 1 from this. So negative 3 minus 1 is x to the negative 4. F prime equals negative 12 times x to the negative 4. Again, coefficient times exponent becomes 3, and now it's going to be x. 1/2 minus 1 is top minus bottom, negative 1/2. Is that derivative? The same thing here. Multiply it out. Who cares? I get negative 4/3. Just a fraction. Now I'm going to do the exponent minus 1, or top minus bottom, negative 1/3. So negative y prime equals negative 4/3 times x to the negative 1/3. And this one is going to be, multiply it out, I get 15/2. Just a fraction. And x raised to, well, let's see, negative 3 minus 1, negative 3 over 2 minus 1 is top minus bottom, or negative 3 minus 2, which is negative 5/2. All these, and that's how we rewrite them. I don't have to rewrite them anything special. I could just leave them as that. And then finally I have this many term function, g. I'm going to rewrite it as 2x to the 3/4 minus 6x to the 2/3 minus 9x to the negative 3 plus 5x to the 4th minus 10. And now I'm going to take its derivative, and its derivative, just one term at a time. 2 times 3/4 is 3/2. X, 3 minus 4 is negative 1/4. Minus 6 times 2/3 is 4. 2 minus 3 is negative 1/3. It becomes positive 27. X to the negative 4. 5 times 4 is plus 20. X to the 3rd. And the derivative of 10, that last number at the end, is just 0. Okay, so we're not doing the long drawn out f of x plus h minus f of x over h. We're learning a little what I call a shortcut rule, the power rule.